LCL, LFC, and EL. Learn how to calculate these special thermodynamic levels and the rest of the thermodynamic alphabet soup in this week's MetPy Monday. Hi, I'm John Lehman, a software engineer at Unidata. Recently, we've spent a decent amount of time talking about thermodynamic diagrams like the skew T, and we haven't really talked about some of the numerical parameters that we often look at along with these. We often want to know things like what's the LCL, or lifted condensation level, the LFC, the level of free convection, or the EL, the equilibrium level. Now, I'm not going to go into detail on what each of these is. That's really something for a thermodynamics course, but I want to show you how to calculate them using MetPy. So the first thing we need to do is get some data. And luckily, this is something that we've covered in a previous MetPy Monday, and it's something that's pretty easy to do with our Siphon library. So let's go ahead and get some data from April 14th, 2012 at 12Z for the OUN station. This happened to be a day where there were quite a few tornadoes in Oklahoma. Okay, so I went ahead and requested our data and pulled out pressure, temperature, and dew point. Those are the three variables that we're going to need to be able to calculate these special levels. Now we need to go ahead and import the MetPy calculation module, which we normally import as mpcalc. So I'm going to import metpy.calc as mpcalc. And then if we look in mpcalc.tab, we can see all of the different methods that we could call here. And let's go ahead and start with LCL. So if we start typing, we see it quickly narrows it down to LCL. I'm going to type the open parenthesis, and then if I hit Shift-Tab, you can see I get a short summary of what this function is expecting us to give it, and a little bit of the docstring. If I wanted to know more, all I have to do is click this little caret here, and we get the entire docstring. So what it tells us is that it's expecting the starting atmospheric pressure, temperature, and dew point. This is a common error that is made, is folks will give the LCL method the entire pressure, temperature, and dew point arrays like that. And when you run it, you see we get a lot of results because we're actually calculating the LCL that starts at every pressure, temperature, and dew point in this profile. Notice it actually wants the starting point. So in this case, I'm going to say that we're starting from the surface. So the 0th value of pressure, temperature, and dew point. If I run it now we get one value, which is what we'd expect for this. We get the pressure and the temperature of the LCL. So 929.7 hectopascals and 17.5 degrees Celsius. One of the other parameters that we talked about was the level of free convection, or the LFC. So likewise, mpcalc, LFC, Shift-Tab, and it says it's going to calculate the level of free convection. It wants pressure, temperature, and dew point. In this case, they are the profiles. So we're going to give it pressure, temperature, and dew point. And we see that it is slightly higher in the atmosphere, which is what we'd expect, 907 hectopascals, 16.6 degrees Celsius. The last special level that we'll talk about is the equilibrium level. If you remember, the LFC is basically when the parcel is going to continue accelerating upward. It's going to freely convect until it gets to the equilibrium level, where it is now the same buoyancy as the surrounding air. If it goes any higher, it's going to tend to get pushed back down. So it is EL, and again, it's going to want the pressure, temperature, and dew point profiles. And as we expect, it's pretty high. So we're looking at 193 hectopascals minus 62.8 Celsius. So one thing that I don't think is appreciated a lot of times in Python is that there is this unpacking syntax. So let's say that we have the LFC and we need to store the pressure and temperature because we're going to do some computation with them, or we're going to plot them. We're going to do something other than just show them on the screen like we did here. Well, we could say LFC equals mpcalc.lfc, and then, well, the 0th element's the pressure, and the 1 element is the temperature. But that's clunky and hard to read, really. So what we can do is actually just say LFC pressure, LFC temperature equals mpcalc.lfc pressure, temperature, dew point. And it knows to unpack those two returns into LFC pressure and LFC temperature. If we want to plot this as a horizontal line on our skew t, which we don't have here, but I will show you, it would look something like skew.ax.ax hline for horizontal line, and then LFC pressure. Now there is a catch to this though. What if the sounding that you've picked doesn't have an LFC? Is the calculation going to error out, or what's going to happen here? Well, let's pick a date. In this case, I'm going to say December 18th at 0Z. I'm just going to rerun these cells. And we can see that we actually get nans, or not a number. So that's telling us that there is no LFC. If we tried to do this plot, it wouldn't work. Well, the easiest way to do this is to do a quick check that's going to say if LFC pressure, then it will plot it. And that works because nans and things like nan evaluate to what is called falsy in Python. So this is going to say if false, well then that block's not going to run. If there's a value there, that's going to evaluate to what we'd call truthy. And so then if there's a value there, go ahead and plot it. That's an easy way to go ahead and make these plotting scripts and data analysis scripts that you're writing robust, is using these truthy and falsy things, and it makes it easy to read. You don't have to say if LFC pressure does not equal nan. No, this evaluates very cleanly for you. I hope that you found this video helpful. If you did, don't forget to subscribe on YouTube so that you can see when videos like this come out every week. You can also follow MetPy on Twitter. We are at MetPy, and we post on the Unidata Facebook page as well. If you have issues or pull requests, you can go to the MetPy GitHub repository, and all of these are linked down below in the video description. Thank you for watching, and we'll see you on the next MetPy Monday.